Welcome to our video on vector calculus operators. Today, we'll explore three fundamental operators: the gradient, divergence, and curl. These operators form the backbone of vector calculus and have numerous applications in physics, engineering, and other fields. Let's start with a high-level overview of these three operators. The gradient takes a scalar field and produces a vector field. The divergence takes a vector field and produces a scalar field. And the curl takes a vector field and produces another vector field, but only in 3 dimensions. Each of these operators gives us important information about rates of change in different contexts. Let's start with the gradient. The gradient operator, denoted as del, takes a scalar field f, which is a function that assigns a scalar value to each point in space, and returns a vector field. Mathematically, for a scalar field f of n variables, the gradient is written as del f equals the vector of partial derivatives, partial f over partial x1, partial f over partial x2, and so on through partial f over partial xn. In 3 dimensions, this would be del f equals the vector of partial f over partial x, partial f over partial y, partial f over partial z. Let's visualize what the gradient means. Imagine a scalar field represented as a landscape, where the height at each point corresponds to the value of the function. The gradient at any point is a vector that points in the direction of the steepest increase of the function. The magnitude of the gradient tells us how quickly the function is increasing in that direction. Let's summarize the key properties of the gradient. It points in the direction of greatest increase of the scalar field. Its magnitude equals the maximum rate of increase. It is perpendicular to the level curves or surfaces where the function value is constant. And it follows the linearity property. The gradient of a sum is the sum of the gradients. Let's work through a simple example. Consider the scalar field f of x, and y equals x squared plus y squared. To find the gradient, we compute the partial derivatives. The partial derivative of f with respect to x is 2x. The partial derivative of f with respect to y is 2y. Therefore, the gradient of f equals the vector 2x, 2y. At any point, this gradient vector points radially outward from the origin, which makes sense because this function represents a paraboloid that increases in all directions from the origin. Now, let's move on to the divergence. The divergence operator, denoted as del dot, takes a vector field and returns a scalar field. For a vector field f with components f1 through fn, the divergence is del dot f equals the sum of the partial derivatives, partial f1 over partial x1 plus partial f2 over partial x2 plus, and so on through partial fn over partial xn. In 3 dimensions, for a vector field with components p, q, and r, this would be del dot f equals partial p over partial x plus partial q over partial y plus partial r over partial z. Let's visualize what divergence means physically. The divergence at a point measures the net outflow of the vector field from a small region around that point. It tells us whether the vector field is expanding, positive divergence, contracting, negative divergence, or neither, zero divergence at that point. Here's a vector field with positive divergence at the center, representing a source or expansion. And here's a vector field with negative divergence at the center, representing a sink or contraction. Finally, here's a field with zero divergence everywhere, also known as a solenoidal or incompressible field. The divergence has several important properties. It's a linear operator. The divergence of a sum is the sum of the divergences. It follows the product rule. The divergence of f times f equals the dot product of the gradient of f with f, plus f times the divergence of f. And it's related to the divergence theorem, also known as Gauss's theorem, which connects the flux through a closed surface to the divergence within the volume. Let's calculate the divergence of a vector field. Consider the vector field f equals the vector x squared, y squared, z squared. To find the divergence, we compute the partial derivatives. The partial derivative of the x component with respect to x is 2x. The partial derivative of the y component with respect to y is 2y. The partial derivative of the z component with respect to z is 2z. Therefore, the divergence of f equals 2x plus 2y plus 2z. This tells us that the divergence is positive in the first octant where x, y, and z are positive, indicating an outward flow or a source-like behavior in that region. Now, let's explore the curl operator. The curl operator, denoted as del cross, takes a vector field and returns another vector field. Unlike the gradient and divergence, the curl is only defined in 3 dimensions. for a vector field F with components P, Q, and R, the curl is del cross F equals the vector, R sub y minus Q sub z, P sub z minus R sub x, Q sub x minus P sub y. This can also be expressed using a determinant-like notation with the del operator, I, j, and k unit vectors. Let's visualize what curl means physically. The curl at a point measures the tendency of the vector field to rotate around that point. It gives both the axis of rotation, the direction of the curl vector, and the magnitude of rotation. Here's a vector field with non-zero curl, representing a rotational pattern around the z-axis. The curl vector would point along the z-axis, with its magnitude indicating the strength of rotation. And here's a vector field with zero curl, known as an irrotational or conservative field. Such fields can be expressed as the gradient of a scalar potential. The curl has several important properties. It's a linear operator. The curl of a sum is the sum of the curls. The divergence of a curl is always zero. Del cross F equals 0. The curl of a gradient is always 0. Del cross del F equals 0. And it's related to Stokes' theorem, which relates the circulation around a closed curve to the curl through the surface it bounds. Let's calculate the curl of a vector field. Consider the vector field F equals the vector negative y, x 0. To find the curl, we compute. The first component is the partial of the z component with respect to y minus the partial of the y component with respect to z. Since our z component is 0 and doesn't depend on y, and our y component doesn't depend on z, this is 0. The second component is the partial of the x component with respect to z minus the partial of the z component with respect to x. Since our x component doesn't depend on z, and our z component is 0, this is also 0. The third component is the partial of the y component with respect to x minus the partial of the x component with respect to y. The y component is x, so its partial with respect to x is 1. The x component is negative y, so its partial with respect to y is negative 1. So 1 minus negative 1 equals 2. Therefore, the curl of F equals the vector 0, 0, 2. This confirms that our vector field has a rotational pattern around the z-axis, with the curl vector pointing along the positive z-axis, consistent with the right-hand rule. Finally, let's discuss some key identities that tie these operators together. 1. The curl of a gradient is always 0. Del cross del F equals 0, 2. The divergence of a curl is always 0. Del cross F equals 0, 3. The divergence of the product of a scalar and vector follows the product rule. Del F equals del F plus F del F4. The curl of the product of a scalar and vector follows a product rule. Del cross F equals del F cross F plus F del cross F5. For the divergence of a cross product, del F cross G equals G del cross F minus F del cross G6. And for the curl of a curl, del cross F equals del F minus del squared F. These operators and identities have countless applications in physics and engineering, including electromagnetism, fluid dynamics, and many other fields.